Hello, everybody. Thanks for tuning in. My name's Frey, and we're going to be going over artificial intelligence and medicine. So AI is the topic. I want to say the views expressed are mine and mine alone. They don't represent any institution or organization. So, what are we talking about? Objectives for today are artificial intelligence, defining it, what is it, um, and discussing examples of artificial intelligence, and then understanding how AI relates to medicine. It's a big hot topic. Okay, so first off, what is artificial intelligence? And there's a lot of different definitions, a lot of views on this. Some people say you can't really define artificial intelligence because it's just a collection of methodologies, tools, statistics. I'm my view is that you can define it, and you can define it in relationship to the community. So my definition of artificial intelligence is AI is a field of research that explores creating and integrating learning machines that improve performance on tasks typically associated with humans. Okay? So that's a mouthful. So let's go into that. So what's learning, first of all? Uh, my view on learning is it's a process for improving performance on tasks. Okay, so that ties in with the human tasks. Because in artificial intelligence, you're improving performance on tasks that typically humans do. So when studying learning, we typically start with a training set followed by evaluation and test of that information that we've trained on. So the training set usually has both the input you want to learn along with the answers that you're interested in. Uh, Example could be input on images of, say, a cat, and then saying, is this a cat or not? These are types of learning tasks you did as a kid, right? When you were a kid, your parents would say, yeah, it's a cat. And eventually you'd point, you say, that's a cat. And they'd go, yes, that's a cat, right? So you learn it and then keep pointing at these things, more instances of cats. And eventually you point at a dog and you say, it's a cat. And your parents go, no, that's a dog, right? So you then learn what are cats and what are other things, right? So this is a process, and we're asking artificial intelligence programs to answer the same question. What is this? I mean, can it learn if it's a cat or not? So so that's the first part, the learning. The other part is the evaluation. For evaluating learning, we usually have a new but related items and present new questions, so to see if the uh, people have generalized on the learning task. You do these things all the time, right? Because you're given books, math books or other books, and you then learn the examples in them, and then you learn how to predict what the answers are, and then you get evaluated on that test, right? So that's a learning process. So same type of things can be done with artificial intelligence programs. So so here we are on a test for an AI. How many cats are in this? Well, that's a different problem than just learning to say it's a cat or not, right? It's got to count them. And then the question is, what was the input that was given, trained on? Was it just that previous image or variations on the previous image of the cat we saw? Artificial intelligence might not be able to identify cats in this picture because they're in a different view, they have different colors. Maybe it wasn't trained on that. But if you have a wide enough set of examples of cats in different positions and the like, it could well identify these, which is a hard task, right? I mean, how many cats are there in this photo? Well, there's some way in the background, behind the door that's hard to see. There's a cat in the foreground that all you're seeing is its tail. Do you count those? And then there's always the cat crossing. Is that a cat or is that a sign of a cat? These are questions we deal with. It really turns into, well, what is the evaluator evaluating when they ask how many cats, right? So that was the learning part of this process. There's also the learning machines, right? So we have learning and we have machines. From a computer science perspective, you can think of machines as programs or apps, right? They take input, such as training sets that we just talked about, and usually loop through these training sets to learn answers to questions. So in the end, you get a representation of what is learned, and it's stored in a mathematical model representation. And this is a big area of research in artificial intelligence. It's basically the core task. What representation is most effective for, representing different types of objects, or representing different types of tasks that we're trying to learn. Okay. So this goes way back, right? If we're talking about this community, well, how old is this community? Well, back in 1950, Alan Turing introduced the concept of learning machines, and made predictions that by 2000 this would be commonplace. Discussion of learning machines would be commonplace. Well, they are. He was right. He was 50 years early, but he was right about it. And he talked about it in terms of this concept of an imitation game, where you would assess the performance of these algorithms on tasks that humans typically do, and then evaluate, did they get it right or not? In other words, are they behaving like a human or not? Well, that was 50 years ago, and you might see this on the internet. Basically, this is a variation on the imitation game, right? It's the I'm not a robot. A site is evaluating you on whether you're a machine or not, right? Much like the imitation game. And it's giving you a task to see if you can identify which squares in this thing have cats in it. And depending on your answer, it says, yeah, you've passed. You're not a robot. You're a human, just as in the imitation game. I do these things every so often. I don't get it right? So I mean, it could be, some. If I click on the cat crossing, was the evaluator saying that was a cat, or was the evaluator saying that's a sign? So, but the point is, this is much like the imitation game. We do it all the time. This is what Alan Turing predicted over 70 years ago. So, a timeline of artificial intelligence and its relationship to machine learning. In my view, it starts with Alan Turing in 1950. That the article that we were just discussing, with imitation games and learning machines. So, and he basically said there's three things that are going to kind of drive this. What are the representations, the algorithms? You can see that as the red line here in this picture. AI publications in medicine, AI in PubMed. You can see it. The number of those things going through the roof as time goes on. Very little of that going on in 1950, but more recently, yes, quite a bit. And so the algorithms have to be developed, and then two other things: memory, and which is so that you can get bigger models, okay, and compute, which means you can get faster models. And these things back in the 50s, I mean, they were so expensive that they go off the chart, right? In the 60s, you're talking around, $100 billion for 1 gigabyte of RAM, right? Even if it existed. I guess it starts existing in the 70s or so on this, in terms of being tracked. In terms of compute, that's a gigaflop of compute power, which is 1 billion floating point operations per second. That's a lot of compute. Again, it was in the hundreds of trillions of dollars, if it even existed in the 50s, which it didn't. But it then comes down in 2018 or so to pennies. Okay, so it's a huge drop, which allows you to get bigger and faster, and that was the breakthrough that we needed, right? Because in around 2006, basically deep learning demonstrated that we could have breakthroughs in image processing that we didn't realize that we could. And then these other two things, I'll just touch on them real briefly. Deep genome, deep phenome, that has to do with its tie into medicine. Phenomes are kind of like diseases, the manifestations of diseases, and genomes are the molecules that make us up in terms of DNA type information. And artificial intelligence is analyzing that to give us insights on our DNA in relationship to disease and phenotype. So, current AI examples. Self-driving cars. Who would have thought? Back in the 50s, they talked about it. They talked about flying cars, but we didn't get that so much. But self-driving cars are now a reality with some glitches. But that's incredible because you need object recognition. You need all of this technology in order to have self-driving cars. And artificial intelligence is now at a level where it makes that somewhat possible. Complex gameplay. Chess, on the timeline, it showed that around 2000, artificial intelligence approaches were beating top chess masters at the game. In the 2000s, we have AlphaGo, right? So, which is an incredibly complex game that was really difficult to crack, and they cracked it with these types of algorithms. Okay, so language models, large language models. This is Chat GPT or Bard, or the ability to type on your computer and interact with something as if it's communicating with you. And the way they do this is they have very fast compute systems that have generated large, in the billions and billions of nodes at this point. You can kind of see, the size of these things are just growing. And it then gives this ability to communicate. Incredible, just an incredible breakthrough that's now currently out there, which then, leads to healthcare, right? If you have algorithms and representations that can represent textual information, I mean, that's what people process in charts for diagnosing diseases and the like, right? It's understanding what these conceptual ideas are in text and then associating them with outcomes. So then this fits into healthcare in terms of early decision making around ailments, help and treatment, better services, giving better experiences, and then going to wearables where you're collecting information on your own system so that you get a better understanding of what's going on with your own health. And artificial intelligence can then analyze that data and help give informative information around that data pattern. So that was kind of medicine, and this is health research. This is a huge breakthrough made by artificial intelligence, where we've now encoded the entire protein universe. Proteins are components that make up organisms, right? They're the little building blocks of life. You can think of them as Lego blocks that kind of snap together and interact in different ways that make up, living beings, right? We now know what those look like in ways that we didn't before, because we can now just look at the DNA sequence and have it tell us, well, this is what this DNA sequence will fold into when it folds into a protein, into a little Lego piece that goes into the organization of organisms. So this has been a whirlwind, but I also want to say, hey, AI is going at whirlwind speeds, right? It's going really fast, and you can be part of it. I definitely, that's a take home of this talk. You can be part of it. You can, like the wearables, right? You can use it to improve your own health and the health of your community. But there are many roles in artificial intelligence. Just instead of just using it, you can be part of the creation for it. So creating programs that improve our understanding of health and human tasks. But there are other roles too, like creating the training sets, making sure people can interact with the AI in an integrated way, testing the AI to make sure it performs in ways that are useful to us, right? So the power to enact meaningful change using AI, it resides with you. And that's the take home of this talk. So I want to acknowledge Barbara Bruns-Frey contributed to the conceptualization of the material and video production of this talk. If you want to cite information from this talk, please use the following citation. And I want to thank the Tech Talk folks for inviting me to this forum. So thank you for watching. Thanks to AIM-Ahead and the Alexandria City Public School Systems, and also George Washington University. Thank you very much. Thanks for watching.